Hello everybody, welcome back to the channel. Grateful to have you all here. Today we're going to be doing 6.1 inverse relations and their graphs. Okay, new unit, new you. As always, if you like the content, hit that subscribe button or the like button, and make sure you smash that bell so you don't miss another video. All right, let's get started. Inverse relations. Which one of these graphs does not belong if Yasmin earns $5 each hour that she babysits? Okay, so in hour one, she obviously earned $5. Let's say in hour two, how much money would she have? She'd have $10. Okay, hour three, $15, four, $20. Okay, now here are two graphs. Which one does not belong? Okay, it's important that we understand what a function is. Okay, a function is when we have an input and an output. We put a number into the function and the function gives us an output. In most cases, we label our input as x and our output as y, or f of x. Okay, so if we plug in a number here, we'll plug in a 1 as our input. If we plug that in, we'd get 2 times 1 plus 1 would give us an output of 3. Okay. The other important thing to understand is when we're graphing functions, our input, or our x, is placed on the horizontal axis or the x-axis. Okay. So if we have an x, y table, dollars is our y value. And in this graph right here, our dollars are on the x-axis. So this graph is not, what do they say? This graph does not belong because here, ours is x, dollars is y, our input is on the x-axis, and our output is on the y-axis. Okay, let's move on. When people first learn to drive, they are often told that the faster they're driving, the longer it will take to stop. So when you're driving on the freeway, you should leave more space between your car and the car in front of you so that when you're slowing down, you don't crash into them, right? Okay, so have you ever wondered if there's a relationship between how fast you're driving and how far you travel before you stop after hitting the brakes? Okay, so that might seem confusing, but let's imagine you're in the car, you slam on the brakes. Depending on how fast you were going would result in how long it takes you to slow down. So think about it for a minute. What factors might make a difference in how far a car travels after hitting the brakes? Okay, let's get a different Christmas color up in here. I think of speed, obviously, as the number one factor in how fast it would take you to slow down. Other things might be road conditions, or maybe even the type of tires or car, I don't know. Speed is the main guy. How fast you're going will result in how long it takes your car to slow down in distance. Okay. Let's see here. There's actually been quite a bit of experimental work done between the speed of a car and braking distance. Yeah, okay, so police have done experiments to figure out how fast it actually takes you to slow down depending on your speed. Okay, flip the page. Imagine you're in your dream car. Maybe it's a Ferrari 550, I guess. A super fast Italian sports car. Okay, this right here is the equation that the police have come up with that will tell us how fast we're going, or depending on how fast we're going, how long it will take us to slow down, where D is distance and S is speed. Okay, so give me a sec here. How many feet should you leave between you and the car in front of you if you're driving 55 miles per hour? Okay, this right here is a speed. So if we have distance as a function of speed, we're going to be plugging in 55 for our equation right here. Wherever there's an S, we're plugging it in. Okay. Now, if you were to plug that in your calculator, you would get 90.75 feet. What does this mean? We inputted 55 miles per hour into our function, and the output is 90 feet. Okay, we'll say 91 feet. So if you're going 55 miles per hour, you need to leave 91 feet in between you and the car in front of you to make sure that you can slow down in enough time. Okay, let's do another one. This time the distance is 100 feet. Just abbreviate that to 0.3 times 100 squared. If you plug that in your calculator, you'd get 300 feet. Okay, so if you're traveling at 100 miles per hour, not many cases where you'd do that, but you'd want to leave at least 300 feet in between you and the car in front of you. Okay, how long is that? If an average car is about 16 feet long, how many car lengths should you have in between you and the car in front of you if you're driving 100 miles per hour? Okay, we just said that that was 300 feet. So if we take 300 feet and divide it by our normal car length of 16 feet, that would leave us with 18.75, or we'll round up to 19 cars in between you and the car in front of you. So if you're driving 100 miles per hour, leave 19 cars in between you and the one in front of you. Okay. It makes sense to a lot of people that if the car is moving at some speed and then goes twice as fast, the braking distance will be twice as far. Is that true? Well, let's test it. We have 100 miles per hour. We just said you'd need 300 feet. Now let's say you're going half that speed at 50 miles per hour. How many feet would you need in between you and the car in front of you? Well, we'll plug it back into this same equation from before. We'll go 0.03 at 50 miles per hour squared would give us a distance of 75 feet. Okay, is that half of 300? No, it's not. Okay, because the function distance as a function of speed at 0.03 speed squared is exponential, meaning that the increase is not linear. The faster you're going, the more distance you'll need in between you and the car in front of you. Okay? All right, so let's graph this relationship. Let's get a nice graph going in here with an x-axis and a y-axis, where our input, remember, goes on the bottom. That is speed. And our output on top. Okay. Now I'll just label this graph here. I'm going to go by 20s. Well, actually, I'll go by 10s and just label every 20th. Okay, and then let's maybe go up by 50s and just write each 100. Okay, let's graph some of this stuff here. Let's put an input into our function. Remember, our function is distance as a function of speed is 0.03 speed squared. Okay, so let's start by inputting maybe 20 miles per hour. Okay, that'll be 0.03 times 20 squared. Okay, if you plug that in your calculator, you will get 12. What 12 what? Well, it is 12 feet. Because we got a distance of 12. If we're going 20 miles per hour, we need to be at least 12 feet behind the car in front of us. Okay, so at 2012, we're going to graph a point. That's going to be just barely right there. 2012. Okay, let's now skip a little bit. Let's plug in 60. If we're going 60 miles per hour, how far would we need to be falling? If you plug that in your calculator, you'll get 108 feet. Okay? That's a lot further than 12 feet. I mean, you're going a lot faster. You're going 40 miles an hour faster, but let's graph that at 60, 108. Okay, let's jump up another 40. Let's go at 100 feet. Okay, now you don't need to replug this in your calculator. We did that up here, look. Distance was 300 feet. If you're going 100 miles per hour, so we'll go 100, 300. Okay, let's do one more. Distance at 140 feet, or miles per hour, my bad, will be 0.03 times 140 squared, and we get 588 feet. Okay, so at 140, we'll be at 588. Okay. Now we'll just connect our dots here. Oh, come on. Okay, good enough. Good enough. See how that's a curved line? It's an exponential function. Okay, let's move on. According to the Ferrari company, not a sponsor of this video, the maximum speed of the car is about 217 miles an hour. Now, this asks you to find a lot of different key features of this graph. Let's just focus on if the car maxes out at 217 miles per hour, how far is the furthest? What is the furthest distance you'd ever have to follow while driving in the Ferrari? So if we do 0.03 times 217 squared, if you plug that in your calculator, we'd get 1,412.67 feet, okay? That is the max. If that car maxes out at 217 miles an hour, you need to be following, or the worst case scenario, you need to be at least 1,400 feet behind the car in front of you. Okay. What if the driver of the Ferrari is cruising along and suddenly hit the brakes to stop because she saw a cat? Okay, she skidded to a stop and fortunately, I hope there aren't any cat lovers watching this video. I'll say unfortunately missed the cat. When she got out of the car, she measured the skid marks left by the car. Sadly, not the cat. Oh, is that too morbid? Okay. So she knew that her braking distance was 31 feet. Okay, so now we're going to do the opposite. If she knew that she broke at 31 feet, how fast was she going? Okay, we're going to plug 31 in for distance as a function of speed. Leaving S alone, because we do not know how fast she was going. That's what we want to know. Okay, now we solve for S. Solve for S. We're going to divide by 0.03, and we'll get 1,033.3 repeating equals S squared. Now, how do you solve for S when it's squared? We're going to square root both sides. Okay, so S equals 32 miles per hour. Okay, we just figured out that because she hit the brakes at 31 feet away from that cat, she was traveling at 32 miles per hour. Only if she was traveling at 33, am I right? Okay, flip the page. If she didn't see the cat until she was 15 feet away, what's the fastest speed she could be traveling before she hit the brakes if she wants to avoid hitting the cat? Okay, again, we're just going to plug in 15 as distance in our equation here, leaving speed alone to figure out how fast if she wants to avoid hitting that cat for some reason. Let's divide by 0.03 on both sides to get 500 equals S squared. And we'll square root that for she needs to be traveling 22.4 miles per hour or less to miss that cat. Okay. All right, now there's a little bit of a typo here. Oh, no, it's been fixed. Okay, this is good. Part of the job of police officers is to investigate traffic accidents to determine what caused the accident and which driver was at fault. Okay, they measure the braking distance, calculate speeds based on this equation we've been using, this function, just like we have been. So let's go back to the Ferrari on a smooth, dry road. Since we know the relationship, create a table that shows the speed of the car was traveling based upon braking distances. Okay, so let's just choose a couple distances here. We'll say maybe we'll go up by 50s. Okay. Now we want to solve for the speed. If we were if we wanted to brake before something in front of us that was 50 feet away, this is in feet, how fast would we need to be going, or even slower? Okay, so we're going to plug in 50 again for distance, 0.03, speed squared, divide by 0.03, and we get, what do we get? 50 divided by 0.03 would be 1666.6 repeating equals s squared, square root both sides. The speed for 50 miles an hour would be 40.8, okay? Okay, now I won't waste your time plugging all those in. Maybe pause the video and try to fill in the rest yourself, but we'll go 57.7, 70.7, 81.6, 91.3, and we already figured out that if you're going 100 miles per hour, you need to be following at least 300 feet. Okay. All right. If you've made it this far in the video, you're a real one. Let me give you a little bit of a reward here. Bless up to you for making it this far in the video. Please consider liking this video if you've liked the content so far. And if not, we'll keep going. Okay. Let's write an equation for this. We've been plugging in distance right here over and over again. Let's see if we can write this equation to be a speed as a function of distance. Okay, so let's take our distance function, and now let's try to get speed all by itself. Okay, so I'm going to divide by 0.03 to get s squared equals distance over 0.03, and to finish this off, we'll square root both sides to get speed as a function of distance would be the square root of our distance over that 0.03, okay? So now if you wanted to figure out how fast you were going based on a certain distance, we could just plug in a certain distance right there, okay? We could get that in one shot in our calculator. Okay, now let's go ahead and graph this guy. So let's give ourselves that x and y axis again. And remember, we put our input on the x-axis. Now this time, our input is different. The thing we're inputting over and over again will be our distance, okay? And our output is going to be speed. Okay, so I'm going to label this the same, but on opposite axes, we're going to have 20, 40. Just going up by hundreds here. We'll cap it at 800. Okay. Now let's get some points graphed here. Okay. Let's look up here. If we were to plug in a distance of 300 feet, what would our speed be? Okay. It would be 100 miles per hour. So at 300, we're going to be at, what is it, 100. Boom. Okay. What did I tell you? At 100, we're going to be at 57.7. So at 100, we're going to be at 57.7. Okay, let's maybe give it one more where we're plugging in a different value. Let's do maybe 600. So now we're doing speed as a function of distance, 600. And we have a different equation here. Our distance is 600 being divided by our 0.03. Okay, give me a sec to plug this into my calculator. You try it on your own as well. See if you get the same thing as I do. We'll get 141 miles per hour, 141.4 miles per hour. Okay, that's a speed as our output. Speed is our output. Okay, 141 at 600. Okay, now our graph looks like this. Okay? Okay. Now let's take a minute to look at both of the graphs we've done. Okay, I think you can see both of them there. Hopefully it's not too small. We've got one that looks like this and one that looks like this. Okay? Where on this one, speed is our input, distance is our output, and on this one, we're the opposite. What do you notice? Okay, the whole point of all of this is that these functions here are inverses, okay? These functions are inverses. They are the exact opposite of each other, where each of each other's inputs is the other one's output. Okay? All right, so you can write that in your own words there, but here, let's get into some actual math. We always label our our inverse as f of negative 1 of x. Okay? It's where our inputs and our outputs flip. Let's do some of this with the tables first. Let's say I have a table here. This is f of x. Let's write a table for our inverse of f of x. Okay? We will have, when our input, or our output is 0.5, we're going to place that as our input. And we should get our other input as our output, okay? It sounds a little bit confusing, but when you insert your other output as your input in this function, you will get the other number. Okay, so do you see what I'm doing? Okay, we'll do one more. Okay, 3 and 2, 4, 3. 5, 5 is the same input output no matter what. 6, 9, 7, 17. Okay, leave that one for you to do on your own if you'd want. Pause the video and try it, or come on over here and let's test. Is this the inverse? No, is this, the inverse of this? To test it, let's just choose an input. Okay, I'm going to do the input for my inverse as 1, where 1 squared plus 3 equals 4. Okay, now notice what I'm going to do. I'm going to use the output we got here as our input in my other function, and we should get 1 if I do this. Okay, 4 squared is 2. Whoops. 4 squared is 2 minus 3. What is 2 minus 3? That is negative 1. Did we get the same input as our output? No. This is not the inverse of this function. Okay? Let's test this guy. I'll use the same input as 1. We do 1 squared again plus 3 equals 4. Now we use that output as our input over here. 4 minus 3 is the square root of 1, which is 1. Is that the same input we used over there? Yes. Yee. Okay. Congrats, you've made it this far. Hope we've become such good friends through this process. Again, consider subscribing. Clicking that bell. Smashing the like button. Okay. Now let's graph the inverse of this. These are super simple. Okay, let's look at these points. This point right here is the point 2, 1. To graph its inverse, we're just going to flip it to 1, 2. Okay, so I'm going to graph 1, 2. That's the inverse of that point. Okay, this point down here is 0, -2. Okay, we're going to flip that to be -2, 0. -2, 0. Okay, now the inverse of this point, which is 3, 5, will be 5, 3. And this one all the way over here, we might be off the graph, but that's 4, 13. Yeah, we're not going to be able to graph that guy, but its inverse would be 13, 4, okay? But notice here, if we connect these dots, that right there is the opposite shape. I mean, it's not perfect, but looks like the opposite shape, okay? This has been a long video. We'll leave it at that. You guys can try these graphs on your own. If not, go do the homework in My Open Math. Hope you've enjoyed this time with me. If you did like the video, please share with a friend. Smash that bell for more videos just like this one. And again, don't forget to subscribe. Thank you, and we'll see you next time.